Assalamu alaikum and welcome to e-learning Al-Noor International School Chemistry course, grade 12. I'm your chemistry teacher Fraz Anjum. This week we will study chapter 25 nuclear chemistry and lesson 2 nuclear transformation. Textbook page numbers 880 till 886. Main objectives of this lesson: describe the type of the decay a radioisotope undergoes, solve the problem that involves the half-life, and identify the two ways of transmutation can occur. So start with the lesson, nuclear stability and decay. What determines the type of decay a radioisotope undergoes? So start with this nuclear force first. The nuclear force is an attractive force that acts between all nuclear particles that are extremely close together, such as proton and neutron in a nucleus. So the attraction between or attractive force between proton and neutron in the nucleus, okay, this is called nuclear force. At this short distance, the nuclear force dominates over the electromagnetic repulsion and holds the nucleus together. The stability of the nucleus depends on the ratio of neutron and to proton. This graph shows the number of neutron versus the number of proton for all known stable nucleus. This is number of neutron and this one is number of proton. Alright, now the region graph in which these points are located is called the band of the stability. So this is called the band of the stability. Okay, the element is the low atomic number, low about 20. This ratio is about 1. So look here, it's nearby this stability. Above the atomic number 20, stable nuclei have more neutron than the proton. So above 20, you can see the number of neutron going to increase. So this side. The nucleus may be unstable and undergo spontaneous decay for different reasons. The neutron to proton ratio in a radioisotope determines the type of decay that occurs. Remember, the neutron to proton ratio, which we showed just now, in a radioisotope determines the type of decay that occurs. So some nuclei are unstable because they have too many neutrons relative to the number of protons. So when one of these nuclei decay, a neutron emits a beta particles. Fast moving electron, beta particles is fast moving electron from the nucleus. Remember again what I said, that if too many neutrons relative to the number of protons, so what happened? Beta particles emission. Okay, and this is called a neutron that emits an electron become a proton. This process is known as beta emission. Okay, this is called beta emission because beta particle is going to be eliminated from the neutron and one proton going to be added. So in beta emission, what happened is neutron to proton, one beta particle emit and one proton going to be added. They increase the number of proton while decreasing the number of neutron. Remember this slide. Okay, now you can see radioisotope that undergoes the beta emission include the following: copper. Okay, in the copper you can see it copper has atomic number 29, it becomes 30, means one proton going to be added, atomic number going to be increased. Okay, and a beta particle eliminate. Same thing here with the carbon. Okay, carbon 14 isotope, it become 6, atomic number 2 7, so carbon become nitrogen. Okay, and one beta particle eliminated here as well. So this is called beta emission. Other nuclei is unstable because they have too few neutrons relative to the number of proton. These nuclei increase their stability by the converting a proton to a neutron. An electron is captured by the nucleus during this process, which is called electron capture. So see here, nickel get the one electron and become cobalt. So change the number of proton, means atomic number going to be changed here. So 28 to 27, here 18 to 17. A positron is a particle that have the mass of an electron but a positive charge. Its symbol is E plus 1. During the positron emission, a proton changes to a neutron just as an electron capture. So boron become beryllium and one positron emit. Same here, oxygen become nitrogen and one positron going to emit. When a proton is converted to a neutron, the atomic number decreases by 1 and the number of neutrons increases by 1. Nuclei that have an atomic number greater than 83 are radioactive. These nuclei have both too many neutrons and too many protons to be stable. Therefore, they undergo radioactive decay. Most of them emits alpha particles. So alpha emission increases the neutrons to proton ratio, which tends to increase the stability of the nucleus. The alpha emission, the mass number decreases by 4 and the atomic number decreases by 2. So you can see here Randon and Ra 88 become 86 and alpha particle going to be eliminated here. Then 90 become 88 and alpha particle going to be eliminated. Recall the conversion of the mass in an important property of chemical reaction. In contrast, the mass is not conserved during the nuclear reaction. An extremely small quantity of the mass is converted into the energy released during the radioactive decay. Checkpoint. During the nuclear decay, if the atomic number decreases by 1 but the mass number is unchanged, the radiation emitted is positron. What is half-life? How much a radioactive sample remains after each half-life. Half-life is the time required to the one of the half of nuclei in the radioisotope sample to decay to the product, means half, not the complete, okay? So after each half-life, half of the original radioactive atom have decayed into the atom of a new. Half-life can be short as a second, as long as a billions of years. So you can see these are the different half-life of the different isotope of elements. Scientists use the half-life of some long-term radioisotope to determine the age of ancient object. Many artificially produced isotopes have short half-life, which make them useful in the nuclear medicine. Short-lived isotopes are not as long-term radiation hazard for patients. Comparing the half-life, uranium-238 decays through the complex series of the unstable isotope to the stable isotope lead-206. So these are the, you can see series of the uranium decays, then become 90, then 90, 91, like this, till stable isotope. So, the age of the uranium containing the minerals can be estimated by the measuring the ratio of uranium 238 to the lead 206. Because of the half-life of uranium 238 is 4.5 times 10 power 9 years, it is possible to use its half-life to date rock as old as the solar system. Uranium compounds are found in the rock in the soil that form from these rocks. How can these uranium compounds lead to the buildup of radon in home and other buildings? Radon gas is product of the decay of the uranium. As the uranium compound in the soil beneath home and building decay, radon is produced by speeds into the structure. Radiocarbon dating. Plants are used carbon dioxide to produce carbon compounds such as glucose. The ratio of carbon-14 to other carbon isotope is constant during the organism's life. When the organism dies, it stops exchanging carbon with the environment and its radioactive carbon-14 atom decay without being replaced. Archaeologists can use this data to estimate when an organism died. Now, exponential decay function. You can use the following equation to calculate how much an isotope will remain after giving number of half-life. Very important equation, remember boy, A is equal to A naught times half n power. A stands for the amount of remaining, so how much amount going to be remain. A stands for initial amount, A naught is initial amount or A initial you can say, and n is stand for the number of half-life. So by using this equation you can calculate it how much amount remains. So the exponent n indicate how many times A naught must be multiplied by the half to determine the A. So this table shows the example of n is equal to 1 and n is equal to 2. The half-life is 0, so A naught times half becomes 0 and 0 is equal to 1, means all the value become 1 times 1, it gives you the same A naught, means initial and remaining will be the same if the half-life is 0. If the half-life is 1, so A naught initial concentration initial amount times half is equal to 1, so become half, initial become half. Now if it's 2, then what will happen, initial times half power 2, half power 2 means half into half. So that's the way you can calculate it. So let's use the example. Carbon 12 emits the beta radiation and decay with the half-life of 5730 years. Assume that you are start with the mass of 2.00 times 10 power negative 12 grams of carbon 12. How long the 3 half-lives? How many grams of isotope remain at the end of 3 half-lives? Okay, two method. Number what is known is given here, and what is unknown, you needed 3 half-life and remaining mass. So multiply the half-life carbon 14 by the total number of half-life. So how many half-life we need? 3. So half-life is 5730 years. So times 3, it gives you 17,190 years. Now for the initial mass, carbon reduced by 1/2 of each half-life, multiply by half 3 times, because 3 half-life we needed. So 2 times 00 times 10 power negative 12 times half times half times half. It gave you 0.25 times 10 power negative 12, and correct significant figure, it gave you 2.50 times 10 power negative 13 gram. This is called the remaining mass. But you can use this method directly by putting the value in the equation. So look here. Now A is equal to, which is remaining, A naught, which is giving the initial amount, times half over n. Okay, n is half-life. So put the values. A naught was what? 2.00 times 10 power negative 12 into half, and how many half-life we needed? 3. Okay, so how you will get? 1/2 times power 3, it give you 1/8. Calculate, it give you the same value what we calculated. Okay, this is the result. Makes sense? Yes. The mass of carbon 12 after the 3 half-life should be 1/8 of the original mass. So if you divide the 2.5 times 10 power negative 3 grams by 2.00 times 10 power negative 12 grams, you will get 12.5 grams, 12.5% or 1/8. The half-life of the phosphorus 32 is 14.3 days. How many milligrams of phosphorus 32 remains after 100.1 days if you begins with the 2.5 milligrams of a radioisotope? Same value. Before this, you have to find out the n. For n, you know how many days you need is 100.1. So 100.1 days times how many days is given? 14.3, and half-life we needed. So when you calculate, you can get the 7 half-lives. Now put the value in it. A, which is remaining, A naught initial, half n. So what is given? 25 milligram. Put here half. How many half-lives? 7. Calculate, you will get 2.0 times 10 power negative 2 milligram. Next topic, transmutation reaction. What are the 2 ways in which transmutation can occur? So for thousands of years, alchemists try to change lead into the gold. Alchemists, Muslim scientists. What they wanted to achieve transmutation? or the conversion of an atom of one element into the atom of another element. Okay, this transmission can occur by the radioactive decay or when particles bombard the nucleus of an atom. The particles may be proton, neutron, alpha particles, or small atoms. Ernest Rutherford performed the earliest artificial transmutation. In 1990, he bombarded nitrogen gas with the alpha particles. Okay, it gives the fluorine unstable, and then quickly fluorine become oxygen. Okay, so the unstable fluorine atom quickly decay to form the stable isotope of oxygen and a proton. Rutherford experiment eventually led to the discovery of proton. So he and other scientists noticed that the pattern as they did different transmutation experiment. Hydrogen nuclei were emitted. Scientists realized that these hydrogen nuclei, which is proton, must be the fundamental role of the atomic structure. James Chadwick's discovery of neutron in 1932 also involved the transmutation experiment. Neutrons were produced when the beryllium-9 was bombarded with the alpha particles. Okay, so you can see here beryllium, when bombardment of alpha particle, it becomes carbon-12 and a neutron going to be released. Element of the atomic number above the 92, the atomic number of uranium are called transuranium elements. So none of these elements occurs in nature, all of them radioactive, and all transuranium element undergoes the transmutation. Transuranium elements are synthesized in nuclear reactor and nuclear accelerator. Reactor produce the beam of the low energy particles. Accelerators are used to increase the speed up of the bombarding particles to very high speed. The European Organization for Nuclear Research, CERN, has a number of accelerators. That figure at the right shows CERN's largest accelerator. When the uranium is bombarded with the relatively slow neutron from the nuclear reactor, some uranium nuclei capture these neutrons. The product uranium form. You can see it's 38 becomes 39. When the 39 radioactive element of the beta particles is the product of isotope artificially radioactive element neptunium form. So 92 become 93. Neptunium is unstable and decay, emitting the beta particles and a second artificial element plutonium. Atomic number 94. So 93 become 94. Now scientists in Berkeley, California synthesized the first two artificial elements in 1940. Since that time, more than 20 additional transuranium elements have been produced artificially. Checkpoint please. Which of the following always change the transmutation occurs? Atomic number. Boys, remember this equation. A is equal to A naught times half n, by which you can calculate the remaining amount. Thank you so much. See you next time.